Thanks so much for that kind introduction, and I'd just like to also start by saying thanks to all the organizers of this conference. It's a great opportunity to come here out to Hamilton and talk about a little bit of the work that I've done in the Burlingame group at the University of Calgary. And specifically, this talk will be focusing on two very similar simple organic dyes where I've just made a 2-atom substitution. And so the last two talks have gone through all of the principles of operation of a dye-sensitized solar cell, so I don't need to belabor that point. But just to the right there, you'll see the two very simple triarylamine-based organic sensitizers, where that X has been substituted for an oxygen and a sulfur. And to really understand why I designed these two particular sensitizers, I just want to talk to you a little bit about some of the losses that can occur in the dye-sensitized solar cell. And the first one really comes down to interfacial recombination between electrons that are injected into TiO2 and with the oxidized species in your redox couple in your electrolyte. In this case, triiodide. And so those hexyl chains off the periphery of this dye, they were introduced. It's been shown over the last 10 years in the literature that when you have long alkyl chains, you can form sort of a monolayer protection that keeps the oxidized species of the electrolyte further away from the TiO2, and thereby shutting down that path a little bit more. Another recombination loss that can occur in the device, which is less prevalent, but it still occurs, is recombination between electrons in TiO2 with your oxidized sensitizer itself. And so that's where this X atom comes into play, the difference between oxygen and sulfur. And the theory behind this was that by introducing a more soft polarizable sulfur group, what you could in theory do was speed up the rate of regeneration, thereby limiting the probability that electrons in TiO2 will recombine with your oxidized sensitizer. And just to go into this in a little bit more detail, shown here, I've shown sort of a catalytic cycle of dye regeneration in the DSSC with a very prototypical dye. And that's shown at the top is N3. And so after photon absorption, electron injection to TiO2, you're obviously left with an oxidized sensitizer. The first equivalent of iodide comes in, and it's thought to form this di-iodide adduct where the electron transfer event has not yet occurred. And it's not until that second iodide equivalent comes in that the electron transfer event occurs. You get your dye regeneration, and you form an equivalent of the iodine radical anion, which quickly disproportionates with another equivalent to form triiodide and iodide, and thus thereby completing your cycle. Now, in 2009, Timothy Privalov did some theoretical calculations of this regeneration cycle with N3. And for the oxidized species of N3, what he found a distinctive interaction between the thiocyanate group of N3 and iodide, in particular with that soft polarizable sulfur group on the NCS ligand. And so that's the real motivation of why I was trying to include the sulfur groups off of these triarylamine dyes. And of course, like any good idea, or at least I thought it was a good idea, this has been done before, most notably by Brian O'Regan and James Durant at Imperial College in London, where they had sort of an N3 derivative where they have substituted off the periphery of that bipyridine, substituting sulfurs with oxygens. And what they found, that these sulfur atoms, they actually increase the rate of interfacial recombination. So it's a bad thing, really. But when you look at this type of molecule and any N3 derivative, the HOMO, or highest occupied molecular orbital, is always delocalized over the ruthenium metal atom and these thiocyanate ligands. And so in theory, that should be the source of the site of regeneration. And so the difference between their system and ours, as you can see through these orbital plots, is that the heteroatom change, you can actually see that there is a sizable orbital coefficient onto the heteroatom, both the oxygen and the sulfur. And so again, where this atom change has occurred, it's at the site of regeneration. So we thought this would be a great system to probe regeneration. And fortunately for the study, both these molecules, they actually feature very similar optical properties, shown on the left on TiO2, and electrochemical properties, where both of these dyes, they oxidize at around 1 volt versus NHE, and the lowest excited state is much more negative than the conduction band of TiO2 for efficient injection. And just to point out, a lot of these measurements were done at Johns Hopkins University in Professor Jerry Meyer's group, and Kahu was the student there that did a lot of these measurements there. And so when we put these in dye-sensitized solar cells, what we found they perform relatively well, kind of exactly what was expected, around 6% power conversion efficiency. Again, these dyes were not designed for high power conversion efficiencies. It was just a simple 2-atom change to really prove a hypothesis. But one thing that we found was that the sulfur derivative consistently displayed a higher open circuit voltage, which was not really anticipated. I thought that the difference, if it was faster regeneration, would be manifested in the current, not the open circuit voltage. And so what Ke did at Johns Hopkins University, he carried out some transient absorption spectroscopy experiments. And so after photon absorption and electron injection, with any dye molecule, you always have an oxidized dye left over, in this case, a radical cation. And so by taking an absorption spectra immediately after electron injection, what you get is you get a transient absorption plot. And there's always this distinctive TPA radical cation absorption. And in this case, it's around 600 nanometers. And so by monitoring the amplitude of that absorption, you can start to get kinetic information about how quickly that TPA radical cation really disappears, either through recombination from electrons in TiO2 with your oxidized dye, or by regeneration from your iodide species in your electrolyte. And so what Ke did was he carried out these experiments on TiO2, where he started to titrate in a known concentration of iodide. And so with the oxygen derivative, just as you'd expect, you see he's monitoring that amplitude, that signal at 600 nanometers, and you see that it starts to decay faster and faster with the more iodide that you add, again, showing that regeneration is occurring. Now, with the same iodide concentrations, when he does this with the sulfur derivative, you can see just visually how much quicker that amplitude decays. And so what you can do is you can plot this kinetic data and extract observable rate laws for the regeneration rate constant. And so the sulfur derivative actually has a 25-fold enhancement of the regeneration rate constant. And so it kind of goes to say to prove our concept that the sulfur group really does play a favorable role for regeneration because it's localized at the site. It's on the site of regeneration, which is the HOMO. But this doesn't necessarily explain, again, why you have a higher open circuit voltage. And so this really comes down to when you look at a DSSC and an IV curve, it depends on where you are on the IV curve of where you're making these measurements. Those past measurements that were shown were done at short circuit. So you're quickly removing all of that current buildup that you have in your TiO2. But when you're actually operating a solar cell, what you end up doing is you're putting a load on the device itself. And what you end up doing is you end up starting to build up some current or electron density in your TiO2. And so when you're going towards your maximum power point, you've already started to build up a little bit more electron density in TiO2. And so what you can do with these devices is you can actually apply a bias to your working electrode to kind of mimic an operating condition if you were to be operating at the maximum power point. And this is exactly what Ke did, where he applied a bias to the TiO2 working electrode to add some electron density to the TiO2 film. And he kept on sweeping it all the way to open circuit just to completely stop the current. And so what he found was that as you apply that bias and you're moving closer towards the open circuit voltage, what he was able to do is determine the regeneration efficiency. And so shown in the red curve is that of the oxygen derivative and the blue curve of the sulfur derivative. So as you can see, as you approach VOC, you're maintaining almost nearly a unity regeneration rate with the sulfur derivative, while the oxygen derivative starts to decrease a little bit, and therefore increasing the population of your oxidized dye on your surface, increasing that rate of recombination as well. And so just to kind of wrap things up a little bit here, over the last couple of years, some very important thermodynamic parameters have been established in the DSSC, where we can now actually kind of make some theoretical estimations of about the highest power conversion efficiencies we can achieve. And so knowing that the voltage, again, is determined by the redox couple of the iodide triiodide electrolyte, and the Fermi level of your TiO2, that will give you your maximum voltage. The redox couple that actually is responsible for dye regeneration is the iodine radical anion redox couple. So you actually have around 400 millivolts of voltage loss, which is unfavorable. And knowing, again, that you need some driving force for that dye regeneration, you can kind of put some estimates on where you can actually get with an iodide-based electrolyte. And so what the study shows here is that maybe if you incorporate atoms that will favor dye regeneration, maybe you can start to approach that iodide iodine radical anion redox couple and start to gain a little bit more in your current. But what's really happening in the field, especially in the last 2 years, is people are starting to move to these one electron redox couples, most notably cobalt polypyrrole types. And so the advantage of these is that you can start to make up some of that voltage loss either as voltage or as current by tailoring your dye as well. And so the beautiful thing about the system, although these molecules were designed to interact specifically with iodide, it appears, at least from the data that we have, is that the self-polarizable nature of that sulfur group also works very favorable with cobalt tris-BP redox couples as well. So that was an extra added bonus for this. So the design of really influencing your sensitizer design and tailoring it to your redox couple for regeneration, it may open up some new opportunities for the field itself. So, and with that, I'd just like to thank some people who helped along the way. Obviously, supervisor, Professor Curtis Burlingett, the current members of the solar crew there, some notable past alumni, and specifically Professor Meyer at Johns Hopkins University in Cook, who did all of the transient absorption measurements. Thank you.